So today we talk about three variable systems. Like two variable systems had two equations, two unknowns. Three variable systems have three equations, three unknowns. We're going to start simple as always. And the reason this example is simple over to the left is that one of the equations actually has a solution contained within it. We are given that the z value is equal to 0. So what we're going to do from here is we're going to find x and y based on that z value. And to do that, we're going to use something called back substitution, where we just substitute the known variable back up into each equation. So in the second equation, I have y plus 2z, and z is 0, equals 4. Therefore, y equals 4. Knowing now that z is equal to 0 and y is equal to 4, I can go back to the first equation and find x. I have the unknown x plus 7 times y, which we now know is 4, minus z, which is 0, equals 12. Therefore, x is going to equal negative 16. So now I have my x, y, and z values. We represent that in what's called an ordered triple of x being negative 16, y being 4, and z being 0. Once again, easiest situation when you have a solution already in the problem. Moving on to the next problem. Now you'll notice this time we have three equations and three unknowns. And each equation has three unknowns in it, so we can't just back substitute. A lot of ways to get these problems done. I'm going to show you one. It's not necessarily the fastest way, but it's for those people who don't see things right off the bat. And this will work pretty much every time. So I label my equations 1, 2, and 3 so we know what we're talking about. And if I look at 1, 2, and 3 real quickly, I see that, hey, all these z's match up. And they'd be really easy to eliminate with very little work by just subtracting one equation from the other. In that case, the z's will all go away. So that's what I'm going to do. I'm going to take two equations. I'm going to take 1 and subtract 2 from it. When I do this, I get 2x minus y plus z equals negative 1. And when I say subtract, that means I'm taking the opposite of every term in the second equation. So that becomes negative x, negative y, negative z, equaling negative 1. Don't forget that negative on the top, or that'll kill you in the end. So I'm going to add these guys up, giving me an x here, negative 2y, z's eliminate out, and that's all equivalent to negative 2. I'm going to do the same now with equations 2 and 3. Notice when we do this, we're going to find something else out that we could have done in the first place. But for those of us just taking a quick glance, this may have been our first step. So if I take 2 and subtract 3 from it, I get x plus y plus z equaling 1. And now I want to take and subtract equation 3 from that, which means, again, taking the opposite of every term. So that's negative x, positive 2y, and negative z. It's all equal to negative 2. So notice what I get when I eliminate these now. The x's go away. I get 3y. The z's go away too, which is great. And I get a negative 1 for my elimination of the two numbers. So what that tells me now is I know the y value. Y is equal to negative 1/3. Solving this may not be pretty, but we'll go through it. So now I have to back substitute. I'm going to go from y equals negative 1/3 into this equation that I found over here. I have an x value minus 2 times the y value of negative 1/3. That's going to equal negative 2. X plus 2/3 is going to equal, I'm going to change this to thirds just for kicks, negative 6/3. And then x will equal negative 8/3. Now from here, I have to take and find my z value. I can plug into any of the 3 equations I want, and I think the easiest one is going to be this middle guy. So I have x being negative 8/3, y being negative 1/3, plus z equals 1. Well, this works out kind of nice because negative 8/3 and negative 1/3 is negative 9/3, which is negative 3, plus z equals 1. Therefore, z is equal to 4. And I have an ordered triple now of negative 8/3, negative 1/3, and 4. Now again, this was a little unique in that when I added 2 of the equations, 2 variables actually went away. That'll happen every once in a while, but not all the time, as you'll see in the next example. So in our next example, again, 3 equations, 3 unknowns in each. I'm going to label each equation, 1, 2, and 3. And you'll notice here something special is also happening, that in equations 1 and 2, I have opposites matching up. So right off the bat, I'm thinking, okay, I got to get rid of my x's. So I'm going to do that. I'm going to take and add equations 1 and 2. When I do that, I'm just going to add them by sight right here and list the answer below. The 3x and the negative 3x goes. 10y and 5y is 15y. And negative 5 and 2 is negative 7z. That's going to equal a negative 1. So next what I have to do is decide, all right, I need to pick 2 of these equations, and I need to eliminate an x variable from the 2. But in order to do so, I'm going to have to multiply. It looks like this is a pretty simple one to do. I'm going to multiply equation 3 by 3 and add that to equation 2. Multiplying equation 3 by 3, I get 3x. I get 6y and negative 3z. That's going to equal negative 6. To that, I'm going to add equation 2, which is negative 3x, positive 5y, and negative 2z, all equaling 5. Add those up to eliminate. You get 11y minus 5z equaling negative 1. Okay, so now what we have is we have 2 equations, 2 unknown left. So this is like what we did the other day with our 2 variable systems. We need to now take and figure out, well, what am I going to do to each of these in order to get a variable to eliminate? Well, I think I'm going to look at the smaller of the 2 numbers, so I'm going to look at the 7z here and the 5z here, and I want to make those opposites. So what I'm going to do is I'm going to multiply this equation by, let's go 5, and I'll multiply this bottom equation over here by negative 7. So I'll get a positive 35 and a negative 35 to cancel out. So 5 times 15, 75. Y. Get negative 35 z equaling negative 5. the bottom equation, I have a negative 77y. I have a positive 35z. Those will eliminate out. And I get positive 7. And this is kind of good because I've got negative 2y right now equaling 2. So y ends up equaling negative 1. Clean. Now I'm going to have to back substitute to find my other variables. So let's do that. Let's take this negative 1 and plug it into, let's plug it into this equation over here. So I'll have 11 times negative 1 minus 5z equaling negative 1. That's negative 5z. This would be a negative 11. Add 11 to the other side, which would give me a positive 10. So z is equal to negative 2. And then I'm going to have to take and find my x value. Again, I can plug the z and the y into any of the three equations. I'm going to pick this bottom one since it's the smallest looking of the bunch. So I have an x plus 2 times the negative 1 for y minus a negative 2 is equal to negative 2. So in this case, this is negative 2 plus 2, which is 0. So x equals negative 2. Nice. And I've got my ordered triple staring at me in the face. I got negative 2 for x, negative 1 for y, and negative 2 for z. But again, this problem was made simpler because two of the variables matched off the bat. So let's move into the hardest example of the day. Now you notice 3 equations, 3 unknowns, no variable already solved for, no matching. Again, we're going to take and begin our process by labeling all of our equations, 1, 2, 3. And I've got to choose a variable I want to eliminate. And to me, really doesn't matter x, y, or z. They look all about as easy as each other to get rid of. So I'm going to just do x. I will choose to take equation 1 and add that to negative 2 times equation 2. Equation 1 is 2x plus y plus 3z equals 9. And negative 2 times equation 2 is negative 2x plus 4y minus 2z equals negative 16. Adding those up and eliminating, I get 5y plus z equals negative 7. Now again, I'm going to have to use 2 equations and figure out how to turn one variable into the opposite of the other. I've got multiple options on this, and I think I'm going to go with 4 times the second equation, add that to the third equation. 4 times the second equation gives me 4x minus 8y plus 4z equals 32. That third equation is negative 4x plus 3y plus 2z, and that's going to equal 4. Add those up. The x's go away. I'm left with negative 5y, which I like, plus 6z. That equals 36. I like this so much because I notice that the negative 5y and the 5y are opposites. So what I'm going to do is add these two equations and just eliminate straight off. So now I have negative 5y plus 6z is equal to 36. So I have in this case 7z is equal to, 29. And z equals 29 over 7, which is going to be nasty when I go back and try to solve this. So let's go ahead and do it. I'll just go straight up into this equation here for my back substitution. I have 5y plus 29 over 7 is equal to, I'm going to change this negative 7 into sevenths, so that's negative 49 over 7. 5y is equal to negative 78 over 7, and it just continues to get worse. And y equals negative 78 over 35. I'm hoping I didn't make a mistake because these numbers are nasty. So let's make that an 8. And then lastly, I'm going to go and take the y and the z values and plug it into the second equation. So here we go. Do that in red so we know it's a little different. So I have x. Let's do this. I have x minus 2 times 78 over 35 plus z value, which is 29 over 7, and that's all supposed to equal 8. All right, so using my calculator to help me out, I get x minus, these two add up to 11 over 35 negative is equal to 8. So I'll kind of be cheap here and say that x then equals 8 and 11 35ths. And now I can just pull out my ordered triple of 8 and 11 35ths, negative 78 over 35, and 29 over 7 for my z value. And that's all I got. Hopefully the problems I assign you are not going to be as ugly as this, but this just gives you an example of what you can do and use your calculator to find the fractional answers and go from there. So here are the problems you need to fill in on the form, and we'll talk about this tomorrow.